Hello everyone. This is the video that I said I would post today. Sorry for the delay though. I will open the homework tomorrow morning. Okay, before we start on what we were talking about today, just as a quick recap, if you remember, in topic 1, we were talking about what we called macro mechanics, right? So in which we said, okay, using your E1, Poisson's ratio, E2, all of these properties were given to you, and using this, we derived relationships between stress and strain, like sigma equals Q bar matrix into strains, right? So this was what we did in topic 1, if you remember. First, we talked about, okay, what are the different materials: isotropic, monoclinic, orthotropic, and we said that composite materials fall in the orthotropic material category, which has 2 or 3 planes of symmetry, and that makes our life really easy. It reduces the number of constants we use, but it was still a 6 by 6 matrix, if you remember. So then we said, okay, let's only consider the plane stress condition, which made it a 2D problem. And so we reduced the matrices. For example, the S matrix, the Q matrix, all of it was reduced to 3 by 3. And then we said, what about if you have an angled lamina, right? So this is when we talked about transformations, bunch of sines and cosines, and that led to us having the S bar, the reduced transformed compliance matrix. I always struggle with this. What? Come back. Okay, for some reason it doesn't want to give me the eraser. And then the Q bar matrix. And then we've jumped over to topic 2, where we said, that's all good, but where do you get these properties from? All right. So then we said, okay, you have the fiber properties, the matrix properties, the fiber volume fractions, the weight fractions, density. And using all of that, we can calculate the different properties. For example, E1 is EFVF plus EMVM. So similarly, we could get all other moduli, E2, nu1, 2, and from that you can get nu2, 1, and then G1, 2, etc. And not only that, we got different strengths. You got the ultimate longitudinal tensile strength, ultimate longitudinal compressive strength, which is in the direction of fibers, and then you have the same things in the direction perpendicular to the fibers. These were called transverse, tensile, and compressive strengths. And of course, you had the ultimate shear strength, right? So we talked about the different strengths. And then we moved on to topic 3, which is where we are now. So this is again, so last part, topic 2, was called micromechanics because you used the constituent properties to calculate your laminar properties. And so we said, okay, so what happens if you combine them? What happens when you have a laminate? So that's when we have been saying, okay, how to calculate if you have loads, N's, and moments, M's, then how do you get to stresses and strains, right? So that's when we have said, or we have found A matrix, which is your extensional stiffness matrix, coupling matrix, and then the bending stiffness matrix. So all of this give us a way to calculate stress, and you know how to get stresses from strains. So today we actually saw how to calculate the elastic moduli for a laminate, which is, for example, X, EY, and then we have GXY, which is the shear modulus, and then you had the Poisson's ratio, nu xy and nu yx, right? All of these related to the height of the laminate or thickness of the laminate, and your A inverse matrix. So this is called the extensional compliance matrix. So in this video, we are going to talk about how to do flexural and hygrothermal constants. So this is what we did in class today. You have the N and M, applied loads, axial loads and moments, which are related to your strains and curvatures using your A, B and D matrices. So if you wanted to get your strains, you have to invert the big 6x6 matrix, and you can divide them into separate parts. So the A star, B star and D star matrices are called the extensional compliance matrix, coupling compliance matrix and bending compliance matrix. So the only thing that you have to be careful of when you invert the big matrix is that the first ones, no problem, right? A, B inverse, but the C star matrix is different. It's a transpose of the B inverse matrix. That is something you have to be careful about. So then we said if it's a symmetric matrix, your B or coupling matrix is 0, which is very good for us. It uncouples our problem. So if you apply axial loads, you only have normal strains. If you apply moments, you only have curvatures. So it's the same thing for the flexural laminates. We are considering symmetric laminate. We hope to do symmetric laminates usually because it uncomplicates a lot of things. Your B is 0, and then the curvatures are equal to just the D inverse matrix multiplied by your moments. Sorry for the interruption. My husband rang or didn't disable the alarm before he opened the door. Okay, so moving on. To get the flexural longitudinal modulus, we do the same thing that we did today morning. We apply a non-zero moment about just the x-axis. The rest of it is 0. So if you write from the matrix, your kappa x equals d11 star multiplied by mx. So then using this, this comes from your bending equation or bending stress formula. If you remember, sigma y or bending stress was equal to, I think when we studied solid mechanics, it was sigma x equals my by I, right? And if you remember, we also calculate what we called curvature 1 by rho, or in this case we denote it using kappa, is equal to m divided by ei. And so from this equation, E equals m by kappa I for a rectangular beam or rectangular cross section, which we assume our composite laminates are, is bh cube by 12. Because we consider loads to be per unit length, B is considered to be 1 here, which means your E equals m by kappa h cubed by 12, or 12 times m divided by kappa h cube. So that's what you have here. And of course you substitute for kappa and you get, as usual, a relationship between, or relationship with h and the D inverse matrix with it. I'm not going to bore you with all the other derivations. You do similar things. You make my non-zero and then you make mxy non-zero, and then you do the same thing for the Poisson's ratios. If you do that, what you get, I have all the relationships in here. So it's EFY is, this was the longitudinal modulus, so that is your flexural transverse modulus, and then you have the flexural shear modulus, and then you have the flexural major Poisson's ratio and minor Poisson's ratio. Of course, you share the same relationship no matter what kind of Poisson's ratio you are looking at. So that was pretty much it. we move on to hygrothermal effects in a laminate. What do we mean by that is, for example, when your aircraft is flying at a very high altitude, it gets icy, it gets very cold. So situations like that lead to having, because of the reduction in temperature, and also there's moisture up there, so that might affect the way our part is behaving. So what happens if there's no constraint? Then it is free to expand. But think of an airplane wing, it is constrained in one direction, and because it's going to be made up of layers that have different orientations, so then it might not all be equally able to move or expand or contract according to the temperature. So that gives rise to residual stresses, because they can't all move equally, right, because of their stiffness variations. And these residual stresses give rise to strains, which are called your mechanical strains. And that is what this matrix is. Mechanical strain in x direction, y direction, and then the shearing mechanical strain. So what does it mean is that we calculate our total strains. We know how to do that. If you subtract your thermal strains, if you have moisture, then you subtract that as well. Just look it up so that I don't make a mistake. Yeah. So So in here you can additionally add minus of epsilon xc, epsilon yc, and gamma xyc, which are the moisture terms. So if you have the moisture strains, you subtract those also. So whatever is remaining gives you the mechanical strains, right? So then we have seen this already. Your thermal strains are thermal coefficients multiplied by the change in temperature. Similarly, your moisture coefficients or moisture strains caused by moisture are equal to the moisture coefficient or coefficient of moisture absorption expansion, beta, multiplied by the amount of or the concentration of moisture absorbed by your layer. So this we have already seen. It's just that we want to account for it numerically. This we know, stresses are equal to Q bar matrix multiplied by strains. Now it's just that it's a combination of thermal and moisture strains. So stresses caused by temperature change and moisture change is equal to the same relationship, Q bar matrix, into the mechanical strains. So those are the ones that is left. Okay. What did I want to say is that if you remember anything from solid mechanics, you would remember that because if you have a structure that looks like this, a cantilever for example, if I induce a temperature change, for example, I'm increasing the temperature, then it is actually free to elongate, right? So this causes no stresses, right? There's definitely a thermal strain because the length is changing, but the stresses we apply is 0, right? In this case, so for example, the N's and M's are 0. N equals, if you remember, it is integral of sigma. For example, Nx is sigma x. We are not multiplying it by the area because this is force per unit length, right? So this is equal to 0. So that's what here we have. If you rewrite it for layer by layer, you separate the integral into integral for the layer. You sum it across all layers, right? So this multiplied by dz equals 0. And then from the previous slide, you can substitute for this matrix as epsilon m, or the mechanical strains was just equal to epsilon x, epsilon y, gamma xy, which is your total strain, minus your thermal strains, x, y, gamma xy, thermal strains, minus epsilon y, oh, my bad, epsilon y, gamma xy, but these are caused by mesh. So we know this already, right? And then we also know that your total strains is actually a combination of mid-plane strains. The knot should be up top here, x, and then epsilon y naught, and the gamma xy naught plus z into kappa x, kappa y, kappa xy. This we already know. So if you make all the substitutions, and if you see, you will have how many terms? 1, 2, 3, and then if you substitute for this, you'll have 1, 2, 3, 4. Because it is equal to 0, you can separate it out like this. So you keep the total strains, epsilon x, epsilon y, gamma xy on one side, and then equate, because you have negative signs here, you take it to the other side, it becomes positive. So this only talks about your alpha strains, but you also definitely have your beta strains as well, which is just equal to, and then you'll have the same thing, plus k equal to 1 to n integral hk minus 1 to hk q bar matrix, and then of course you'll have the beta x, beta y, beta xy for each layer multiplied by del c multiplied by the whole thing dz, right? Here dz. So it's the same relationship you have seen, A matrix into mid-plane strains plus B matrix into your kappas gives you your N matrix. It's just that now you can actually separate them into thermal strains or thermal loads and thermal or moisture loads. It's the same thing for bending as well. You can have bending moments caused by the temperature change and bending moments caused by or torsion, if you talk about MXY, all kinds of moments that are caused by moisture absorption, right? So this is the only change if you want to include hygrothermal effects. It's no longer just N and M's. You'll have to account for thermal and moisture loads as well. So NT is just del T, which is going to be a constant value. And then inside the summation, you have layer by layer Q bar into the thermal coefficient of thermal expansion multiplied by your HK minus HK minus 1. Similarly, you have for NC, which are the moisture loads. So you have del C, and it's the same thing, sigma k equal to 1 to n, the Q bar matrix, and then you have beta x, beta y, beta xy for that particular layer. It's the same hk minus hk minus 1. If you talk about moments, then for the thermal moments, you have half times del T, inside the summation Q bar, alphas, hk square minus hk minus 1 square. The half comes from the integration process. When you integrate z dz, you get z square by 2, right? Where it comes from, it's the same thing for your moments or rotation caused by moisture absorption, half del C, sigma k equal to 1 to n, Q bar matrix, and then it's the same beta x, beta y, beta xy for the kth layer, hk square minus hk minus 1 square, right? So these are the loads that are caused, or these are called fictitious loads, because of course fictitious loads, because there's no actual force that we are applying on the structure, right? But it still causes strains. So these are the loads that, if applied, would cause the same kind of strains. So that is what you use. So if you have a combination of mechanical loads and hygrothermal loads, so then you calculate the NTs, MTs, NCs, MCs, and then combine all of this to calculate your strains. And then from the strains you get stresses. Again, if you remember, the strains, just the mechanical strains, for example, all the mechanical gamma xy equals your total strains, which you can calculate using the N and M's. And then of course you have the strains caused by temperature change, and then moisture absorption. This was from our first slide for the kth layer. And from this you can find stresses, global stresses for the kth layer by multiplying Q bar and your epsilon M's, right? So the fictitious hydrothermal loads given in the previous equations, we can apply mechanically to get the same stresses and strains as the hygrothermal loads. So if you have both mechanical and hygrothermal loads, you can add the mechanical loads to the fictitious hygrothermal loads to calculate the ply-by-ply stresses and strains. Or you can apply them separately and then add the stresses together at last. So this is it for this topic. The hygrothermal loads, do not worry about them. You can maybe look at example 4.5 for it to make more sense numerically. People prefer numbers always, but it's not very complicated. Please ask me questions if you have them. And just as a reminder, the MATLAB assignment is due on number 5. The homework is due on Tuesday, number 4, and I will open the quiz next Wednesday. Tuesday, this is Wednesday, this is Wednesday, and of course the lab is due on Sunday. Alright, with that I'm done. Please go through it, please do the homework. The quiz might be harder for this one, so take some effort, study, go through your textbook, and then ask me questions. I will see you next week.